training powerful deep learning models from scratch often demands immense datasets, computational resources, and time. But what if there was a way to bypass this extensive training, achieving remarkable results with significantly less data and effort? This is the core promise of transfer learning, a paradigm shift accelerating AI development across industries. At its heart, transfer learning is the practice of taking a model pre-trained on a vast, general dataset for a specific task and repurposing it for a new, related task. Think of it like a skilled chef moving to a new restaurant. They already possess fundamental cooking techniques and knowledge of ingredients, requiring only a short period to adapt to a new menu, rather than learning to cook from zero. The pre-trained model acts as this experienced foundation, equipped with learned features that are broadly applicable. The advantages of transfer learning are compelling. Firstly, it drastically reduces the amount of labeled data required for new tasks, overcoming a major bottleneck in many AI projects. Secondly, it significantly cuts down training time and computational costs, as you're starting from an already optimized point. Finally, models trained with this approach often achieve higher performance, especially on smaller datasets, because they leverage the robust feature representations learned from the initial, larger dataset. One primary technique in transfer learning is feature extraction. Here, you take a pre-trained neural network, typically trained on a massive dataset like ImageNet for image classification, and simply remove its final classification layers. The remaining layers act as a powerful feature extractor. When you feed your new, smaller dataset through this modified network, it outputs rich, high-level features. You then train a simple classifier, like a logistic regression or a small neural network, on these extracted features to solve your specific task. The pre-trained network's weights remain frozen. Another powerful technique is fine-tuning. This goes a step further than feature extraction. Instead of just using the pre-trained model as a fixed feature extractor, you unfreeze some or all of its layers and continue training the entire network, or parts of it, on your new dataset. This allows the model to subtly adjust its learned features to better suit the nuances of your specific task. Fine-tuning often yields superior results but requires careful hyperparameter tuning to avoid overfitting, especially with very small datasets. Transfer learning has revolutionized fields like computer vision and natural language processing. In computer vision, models like VGG, ResNet, or EfficientNet, pre-trained on millions of images, are routinely fine-tuned for diverse tasks such as medical image diagnosis, object detection in autonomous vehicles, or specific image classification problems. For NLP, pre-trained large language models such as BERT, GPT, or Roberta, which have learned complex language patterns from vast text corpora, are adapted for sentiment analysis, text summarization, machine translation, and question answering with impressive efficiency. In essence, transfer learning democratizes deep learning, making powerful AI models accessible and deployable even for those without vast data archives or supercomputing resources. By standing on the shoulders of pre-trained giants, we can rapidly develop sophisticated solutions, pushing the boundaries of what's possible in AI and accelerating innovation across countless applications.